Hello there. In this lecture, we are going to study about what is electric flux, right? Now, to explain the meaning of electric flux, I'd like you to imagine how water or how rain falls on one fine monsoon evening, right? So, think about raindrops falling, right, at some place, and you are standing with a unique design umbrella, right? Let's say that the umbrella that you are holding in your hand is having a rectangular shape instead of the usual shape like this, right? Let's say this umbrella is flat, okay, and its handle is very peculiar. Its handle is like this, right, as if it's an arrow, right? So this is an umbrella designed clearly by a physicist, right? Because this umbrella shows some character, some properties like a vector, right? Well, so let's name it vectorella, okay? बहुत बारिश हो रही थी, मैंने सोचा एक वेक्टरेला बना लेता हूँ और मैं बारिश में चला गया, मैं भीग नहीं रहा हूँ. But now if you think of what happens if you tilt it, right? Suddenly the idea of flux will start coming in your mind. Well, if you are going to tilt it, the amount of water falling on that umbrella is going to decrease, right? So that is exactly related to flux. So let me write down the definition. Our basic idea about flux means to pass through. Flux means to pass through, right? So in our case, raindrops are falling vertically downwards, let's say, and if you are going to tilt the umbrella, you hold it from here and you tilt it, what you are going to see is that now the amount of water falling on that in some given time, falling on the umbrella, will decrease, right? So that is what flux is, right? So let's take an idea over here that if you want to find out amount of water falling on this vectorella in some given time, right, in some fixed time, if you want to find out how much water falls on this vectorella, then I'm sure you understand that it depends on three factors. Let's see what these three are. First one, it depends on intensity, or you could say magnitude. I'm not saying speed, that's not the word I want to use, of rainfall. That is, if there is heavy rainfall, obviously in 1 second or in some given time, there's going to be more water falling on that umbrella. Now, the second thing that it depends on is obviously the area of that vectorella, right, or the area of that surface. I'm sure you would realize it. Oh, if instead of this there was a bigger surface, right, if you compare these two situations, obviously more water is going to fall for the case where the surface is larger. So it depends on area, or rather I could say surface area of that vectorella, right? And the third thing, which might not come to your mind very easily, is the angle between the handle and direction of rainfall. Think about that as well. At this moment, the way I've drawn it, it looks as if the raindrops are falling vertical, so they are falling in downward direction, right? And the arrow or the handle is also pointing downwards. So in that case, you are going to receive maximum amount of water falling on that umbrella, correct? But instead of that, if it was tilted, that is, as the angle will increase, ultimately, let's say we go to the angle 90, like this, and if the raindrops are falling vertical, right, and there is no wind, then there is hardly any water falling on this rectangular surface, right? So we are clearly seeing that when the angle is 0, you are getting maximum, and when the angle is 90, angle between rainfall's direction and angle between handle's direction. I mean angle between rainfall and handle, right? So when that happens, when this angle is 90, you are going to receive nearly 0, right? You are going to receive nearly 0 water onto this rectangular surface. So both these observations clearly call for cos theta. I hope you realize why. Like I said, when it's 0, when the angle is 0, it's maximum 1. But when the angle is 90, the value is 0. So that's cos 90 is 0, right? So ultimately, I hope you realize that the amount of water depends on these 3 things, right? How much water passes or falls on this surface, right? That depends on these 3 factors. Well, if you understand these 3 factors, I'd say you have almost understood what is electric flux. Now let's go to electric field. So consider that there is some electric field. Right now I'm assuming that the field is uniform, okay, to keep it very simple. So assume that there is some uniform electric field in this region. Let's say it is E vector, okay, and here is some surface, right, with some surface area S, let's say, okay. So now I want to find out how much of the electric field passes through this surface, right? So that's obviously called electric flux, right? So in that case, this thing, the flux, should depend on the magnitude of the electric field, right? Again, hopefully you remember that electric field lines are close to each other. That actually means that the electric field is stronger or has more magnitude, right? So if the magnitude of electric field is more field or more field lines are going to pass through this surface. The second thing that it should depend on is obviously the surface area. If the surface area is bigger, more electric field or field lines will pass through it. And finally, the angle, right? The way I've drawn it, if you think of a vector, again, over there we had a handle. Over here we don't have a handle, right? Surfaces don't have a handle. So we have to think of a vector that goes out perpendicular from this surface, like this, right? And that is that angle between, like I said, we have to take a vector that goes out perpendicular to this surface. So I can say the angle between the electric field vector and the normal direction. I hope you are not confused about this terminology. Normal, that is perpendicular, right? So this is the angle between the electric field and the normal direction. Normal to what? Normal to the surface, right? Okay, so it depends on these 3 things. Now, how do we formalize it? How do we write it in form of an equation? Well, this is how. Electric flux phi, the symbol of electric flux is phi, is equal to E vector dot Sn vector, right? Sn vector, S stands for surface area and n vector stands for, or n hat stands for the normal direction, right? You can also combine it and write it like this, right? Okay, you can also combine it and write it like this, because if you write it this way, then S vector is nothing but the area vector of that surface. So what we are doing is we are defining something called area vector. So what is an area vector? This is the area vector. Area vector is a vector whose magnitude is S, that is surface area, right? It is a vector with magnitude equal to surface area, all right? And what about its direction? Well, its direction is normal, that is perpendicular to that surface. Okay, right? Again, we have taken S vector as the area vector of that surface, And S vector is a vector whose magnitude is the surface area S, and the direction is the normal direction, right? So obviously this gives you E S cos theta. I don't think you have any problems with that, because when we take a dot product, we get cos theta, right? So A vector dot B vector is AB cos theta. So that's why you can see the flux should depend on three things. One, magnitude of the electric field, as you can see over here. Second, surface area. Obviously, bigger the surface, more the flux passing through it. And the third one is it depends on this angle, right? That is, it depends on cos theta, where theta, again, you should not forget, is this. Theta is the angle between electric field vector and the surface area vector. That means it is the angle between electric field vector and the normal direction. Okay, right? So this is the formula of electric flux. Again, flux means how much is passing through. So when we say electric flux, it means how much of the electric field goes through that particular surface, right? Okay, so I'm sure you realize that if we are going to turn that surface at 90 degrees, right? So let's say it's something like this. So let's say this is a surface, right? Okay, its area vector is in this direction, right? As usual, normal to the surface, and the electric field is in this direction. Uniform, suppose it's uniform again. I'm keeping it simple. Let's say it's uniform. Right? So this is a uniform electric field in that direction, parallel to the surface. In such a case, what happens is that the angle theta, again between S vector and E vector, is 90. So the flux through the surface is 0, right? This is exactly the case like this, right? So what this means is that if you want intuition about electric flux, you should use the case or the example of rainfall falling on a flat umbrella with a handle. Right? That handle actually indicates the normal direction. I hope now you do realize why I thought of such an example, right? So that is what is electric flux. Important things, again, that formula. So you should remember that if the surface is flat and the field is uniform, then you can easily find out the electric flux using E vector dot S vector. S vector is the area vector. You can also write it like this, okay, but use for uniform field and flat surface. Don't forget that. Use this formula for uniform field and flat surface. What if E is not uniform, or what if the surface is curved? We'll see.